Hello, I am Shelby Schumacher, and I'm going to be talking about compressible fluid flow. And for this example, we have a car tire that had a nail in it, but the nail was removed, and so all of the air escapes. And then if we blow this picture up of the hole, we see that this can be treated as a nozzle because it's going from a larger area of the tire and out through this smaller area into the atmosphere. And so one of the questions is, what happens to the mass flow rate if just the area is decreased? And so what's driving this flow is that there's a decrease in area. And so what's going to happen to the mass flow rate? And an important thing to keep in mind about this problem is that air is an ideal gas, it is compressible, and that this process is isentropic. And from there, we can assume that this is a converging nozzle. And if we want to look at what the flow is doing by how the area changes, then it's also necessary that the internal pressure for the tire is constant. And so one way that the question is devised to make this happen is that you're trying to pump up your tire with an air compressor even though there's a hole in it. And so what that does is creates a constant internal pressure because it's always being resupplied. And so we know that since this is a converging nozzle, the flow is going to choke at some point because it's going from the large area to the small and then out to the atmosphere, like in this picture. And so at Mach 1, where the flow is choked, the change in mass flow rate with respect to a change in Mach number is equal to 0. And what that means is that this is our maximum flow rate of mass. And so any downstream pressure, so long as the upstream pressure is constant, will not change the mass flow rate. So the mass flow rate is going to increase with a decrease in pressure to a certain point where it reaches the choking pressure, and then it will flatten out and be constant. And so what this tells us is that this mass flow rate at the choking pressure is the best we can do by only changing the exit velocity / the area. And then the second question asks about if you have a fluid that is flowing and it's brought to a stop, where does the energy go? And so for this example, the question tells you to assume that the velocity at the entrance is negligible, and so that means that it's stagnant. And so then from there, we have an equation for the stagnation enthalpy, which is this. And so where the energy goes is told by us directly from this equation. And so we know that the total energy is going to be in the form of internal pressure and kinetic energy. And this is done when a fluid is brought to a rest adiabatically. Thank you for listening. That's all.